say that chemistry's my hustle. Your brain is like a muscle. So settle in because it's time to flex.
Hey everybody. All right, so we're starting a new unit out, and in this unit we're talking about gas chemistry. And in this video I'm going to be going over 4 definitions, and if you know the simple working definitions for these 4 different keywords, you basically can explain all of these relationships. So we've got volume, number of moles, temperature, and pressure. As you can see, I already have some of the notes already filled out. So have your packet out. Be ready to follow along. We're going to start with volume here. So the book definition, if you looked up the book definition of volume, or I'll call this the formal definition, it is the amount of space occupied by a substance. We're basically going to look at some examples, what it looks like at the particle level, until we get to the simple working definition. And this is the one that I want you to focus in on. First, let's think about an example of volume. I think of like, you guys have all seen dunk tanks at some point or another. Here's a dunk tank, and let's say it's a really big dunk tank because I'm going to have a little diving board here, and there's a person on top. A little person about to jump into the dunk tank. Let's say that the water level inside this dunk tank is 400 liters. And once this person jumps into the dunk tank, the water level goes up. And that's because this person, they have their body takes up space. So now the water level in the dunk tank is 600 liters. We could determine the volume of this person by taking the final volume minus the initial volume. This is determining volumes through water displacement, and they have a volume of 200 liters. We're talking about the same type of volume when we're talking about gases, but unfortunately we can't see gas particles like we can see people. So in the bottom left box here for particle level, draw 2 boxes. If you can make them 3D, even better. And I've labeled one as low volume and the other is high volume. Now I'm going to add some gas particles. For the purpose of this, I'm just going to draw some dots that represent gas particles. Just know that I'm simplifying it a little bit. And each box, there's 3 gas particles. The difference between these 2 boxes is that one box is obviously bigger than the other. That is the volume that the particles have to move around in. So when we're talking about gases and you're thinking about volume, the simple definition that I'd like you to think about, it actually sounds pretty close to the book definition for this one. It's the amount of space that the particles move around in. There we go. The amount of space the particles move around in. Now let's talk about number of moles. The book definition of moles is not a very useful one when we talk about gas chemistry. It's the number of atoms in 12 grams of the isotope carbon-12. That's actually how a mole was determined. And we know this number to be equal to 6.022 times 10 to the 23rd, and I'm going to say particles. Another fun little fact, at 0 degrees Celsius, so at a specific temperature and a specific pressure, 1 atmosphere, more on pressure later, 1 mole equals 22.4 liters. So it takes up a certain amount of space. So let's draw what this would look like at the particle level. Remember, we can't see this with our own eyes, so we're imagining what it would look like. In the box on the left-hand side, let's draw 3 particles. And on the right-hand side, let's draw 6. And that represents that we have more particles of gas when it's a higher number of moles. When you hear moles in the context of gas chemistry, all I want you to be thinking about is the number of gas particles. If there's lots of gas particles, that means we have a higher number of moles of gas. Okay, on to our third definition, temperature. The book definition for temperature is a measure of the average kinetic energy of a substance. So, you might be used to a temperature like on a thermometer. And that temperature, you might be more familiar with things like Fahrenheit temperature, right? If it's 50 degrees out. Well, when we say kinetic energy, let's actually write down the equation for that. Kinetic energy is equal to 1/2 mv squared. And notably, the v there stands for velocity, like speed. How fast are the particles moving? So in this next particle level image, we need a way of showing some particles moving slower and some particles moving faster. On the left-hand box, well, let's start by just drawing equal number of particles on both sides. Let's do 3 particles. The difference, though, is that on the left-hand side, they're going to have a low temperature, so we need a way of showing that. Let's add some arrows to represent their speed. Oops. On the right-hand side, since it's a higher temperature, the gases are moving faster. So I'm going to use longer arrows to represent that. Like that. So, sure, we think of temperatures in terms of Fahrenheit and Celsius, but I want you to think qualitatively about what's happening at the particle level. A good working definition for gas chemistry is that temperature is really the speed of the gas particles. I'm going to add a word in there, the average speed of the gas particles, because some particles might be moving faster than others at the same temperature, but on average, they're going to have a higher temperature, or a higher speed, I mean. Okay, our last unit or term that we're going to cover is pressure. It's a very important one when it comes to gases. Pressure is defined, the book definition is the force per unit area on a surface. Think of the last time that you saw a flat tire. I had one not too long ago. And turns out I had a hole in the sidewall. And that's unfortunate because that means you have to get a new tire. Let's see. I'm not the best drawer, but you get the idea. Let's say we put that tire, let's say we had a pump, right? It's going to look like a bike pump. There we go. And on that bike pump, there's probably going to be some sort of gauge. I'm just going to blow that gauge up a little bit so you can see it. You might see a unit of pressure on there, PSI. It's not used very often in chemistry. We have other units for pressure that we use, but they're all saying the same idea. So you might see like 0, 15, 30. And if this is truly a flat tire, we're probably going to see that gauge close to 0. What does PSI mean? What does it stand for? Well, pounds is the P part, and it's pounds per square inch. Let's break that down. Pounds. Pounds is a unit of force. And per square inch, the square inch part, that is an area. We're talking about the force of these particles per square inch, an area of the tire in this case. So how could we draw that at the particle level? We need a way of showing force. Let's draw let's just do 3 moles of gas again. And we need to show more force on the gas, with the gas particles on the right-hand side. So the left-hand side, I'm going to draw some arrows. Like so. Now, why might the particles on the right-hand side have a higher pressure? Well, maybe the temperature is higher. That would cause them to collide more with each other and the walls of the container. Notice there's more collisions on the right-hand side because, well, it's a result of a higher temperature, but it's showing more pressure. So our working definition in this case, sure, we're talking force per unit area, but if we were to see it with our eyes, if we were able to see the gas particles, we're talking about the number of gas particle collisions. Now, using these 4 working definitions that we just looked through, you're going to be working on a simulation. I'm going to show you how to get started. I'm even going to work through the first one with you. So the links here, you could also find it just by going into Google and typing in gas PHET, P-H-E-T, gas properties. And that will take you to this here. And I'm going to press the play button. And then click on ideal. We're talking about ideal gases here. And in the directions it says pump some gas particles in there. I'm going to pump some in. I'm even going to do 2 pumps here. And for this first simulation, we want that pressure to be constant first. Now you've got some controls here. You can actually change the volume of the box like that. You can actually let some gas particles out by opening up the door on the top side. That. And you can heat it or cool it up with that bottom thing. But for this first one, if I go back, it says, once we have some particles in there, we are going to, after the pressure is constant, click pressure. We're going to want the pressure to be constant. And let's see what happens now if I heat the container up. So I'm going to increase temperature. Let's see what happens to the volume. Notice the volume got larger. If I cool it down, the volume gets smaller. Okay, so going back here, we're going to circle what happened. When temperature increased, volume increased. When temperature decreased, volume decreased. Since they both went up together and they both went down together, that would be considered a direct relationship. But the explaining part is really important here. That's really what this learning target's getting at. Being able to explain the relationship in terms of those working definitions that we have. So, how could we relate temperature and volume using their their working definitions. I'm going to start with temperature. If we increase the temperature, the particles will move faster. So, let's see. When the particles move faster, they will cause, in this case we have an expandable container. Not all containers are expandable, but since I set pressure to be constant, it is expandable. When the particles move faster, it will cause the expandable container to increase in volume in order, see, and now I have to use the definition of volume in order to make more room for the faster particles. Let me break down this explanation for you. We talked about increasing temperature, and then we defined it by saying they move faster. And then we talked about an increase in volume, and we talked about what that means. More room for the faster particles. So if you are having trouble explaining these, always go back to the definition of the two things that we're trying to relate together. In this case, this was 12.1b. I know how volume and temperature are related. And yeah, we're just relating those two together. So we've got three more. You're going to be doing volume and pressure, temperature and pressure, and amount and pressure. Remember to read the little directions afterwards, because that's going to tell you what you need to do next to make the simulation work for you.